In the world of computers, things are often seen in absolutes. It's a world of yes or no, true or false, a clear distinction between 1 and 0. This binary approach has been the foundation of computing for decades. But the real world, the one we live in, is rarely so clear-cut. It's full of maybes, uncertainties, and shades of gray. Is it hot outside? Maybe. It depends on your perspective, your location, and even your own personal tolerance. Is it cloudy today? Sort of. There are patches of blue sky, but also some ominous-looking clouds gathering on the horizon. Soft computing is a revolutionary approach that lets computers handle this inherent uncertainty, allowing them to make sense of the world's ambiguities. It allows machines to reason and make decisions just like we do, even when faced with incomplete or imprecise information. Instead of demanding perfect answers and absolute certainty, it works with imprecise, messy information, embracing the nuances and complexities of real-world data. Imagine trying to describe a sunset as orangey pink, a blend of colors that defies simple categorization. Soft computing helps machines understand that kind of nuanced description, bridging the gap between human perception and computer logic. This approach is crucial for a wide range of tasks, including speech recognition, facial recognition, and medical diagnosis, especially in situations where data isn't always clear and definitive. In these complex scenarios, we need computers to make educated guesses, to infer meaning from incomplete information. We need them to persevere and find solutions, not just give up when things aren't perfect. Soft computing represents a fundamental shift away from rigid rules and predefined algorithms. Instead, we build systems that learn and adapt, constantly refining their understanding of the world, and the most important tool in this powerful new toolbox, it's a concept inspired directly by the human brain, the ultimate information processing machine. So let's start by exploring its simplest building block and see how it all comes together. Meet the Perceptron, a tiny decision maker. It takes in information, weighs each piece, and makes a yes or no call. Think of it like a concert gatekeeper. Do you have a ticket? Are you old enough? Each answer matters differently. The Perceptron adds up these weighted inputs and compares the total to a threshold. Above the threshold? Yes. Below? No. For example, should you take an umbrella? If the forecast says rain, that input gets more weight. Alone, a Perceptron can only solve simple problems, like separating big dogs from small dogs. But real-world problems are messier. You can't define a cat with one rule. So what if we use a whole team of Perceptrons? That's where the magic begins. Let's see how they work together. One Perceptron is limited, so we connect many together, forming a multi-layer Perceptron or MLP. Picture an assembly line. The input layer takes in raw data, like pixels from a photo. Hidden layers process this data, each finding simple patterns, edges, curves, colors. Each layer passes its findings to the next, building up more complex shapes and features. One layer might spot an ear, another a whisker. This teamwork creates a hierarchy of understanding. Finally, the output layer makes the decision, cat, dog, or hamster. The strongest signal wins. By stacking simple units in layers, MLPs solve problems no single Perceptron could handle. This layered teamwork is the secret to their power. But how do they learn what to look for? MLPs start out completely clueless, like a blank slate ready to be written upon. They have no pre-existing knowledge or understanding of the world. Their weights are initially random, much like the connections in a newborn's brain, before it begins to process visual information. These random weights determine how the network will initially respond to different inputs. They learn and evolve through a process called training, where we show them thousands upon thousands of examples, each meticulously labeled with the correct answer. This is supervised learning at its core. At first, inevitably, they guess wrong. Their predictions are often far from the mark, but every single mistake is actually a valuable lesson in disguise. The error, the difference between the guess and the right answer, is carefully measured and then sent backward through the entire network, a crucial process called backpropagation. This is where the magic truly happens. Each individual Perceptron or node tweaks its internal weights, learning from its specific part in the overall mistake. If a connection helped nudge the answer in the right direction, even slightly, its connections are strengthened, making it more influential in the future. This learning cycle repeats over and over, refining the network with each iteration. Gradually, almost organically, the network organizes itself. Some Perceptrons become specialized to spot loops, while others focus on identifying sharp angles or subtle curves. The MLP, once a blank slate, becomes a sophisticated pattern detector, expertly learning to recognize handwriting, faces, or virtually anything else, all without ever being explicitly told the underlying rules. It's essentially trial and error, but executed at lightning speed by powerful computers. And that's fundamentally how MLPs learn to see and understand the world around them. Now let's delve deeper and see why this remarkable ability changes absolutely everything. The true power of MLPs, or multi-layer perceptrons, stems from their architectural depth. It's not just about having a single layer making decisions. Each successive layer learns increasingly abstract and complex features from the data it's fed. This hierarchical learning is what sets them apart. Early layers act like basic sensory organs, finding simple elements like edges and colors in images. Then, deeper layers intelligently combine these fundamental elements into more complex shapes and ultimately, recognizable objects. This sophisticated process is what lets MLPs tackle a wide array of real-world problems, from accurately recognizing faces in a crowd to seamlessly translating languages in real time, assisting in complex medical image analysis to aid in diagnoses, and even attempting to predict the volatile fluctuations of the stock market, to enabling the development of sophisticated self-driving cars, and so much more. They're essentially the intelligent engines driving much of our modern smart tech, powering systems that recommend movies tailored to your taste, and assisting doctors in spotting diseases with greater accuracy, and playing a crucial role in keeping us all safe while we're on the road. By being trained on vast quantities of examples, MLPs effectively teach themselves to identify and understand complex patterns hidden within messy and unstructured data. They've truly unlocked a new era, a revolution of intelligent machines that can perceive and interact with the world around them in ways that are becoming increasingly similar to how humans do. From accurately recognizing your unique handwriting to taking the wheel and safely driving a car, MLPs are becoming increasingly ubiquitous. They are quite literally everywhere. The seemingly simple idea of stacking these decision-making layers one on top of the other has fundamentally changed the landscape of computing forever. That's the real magic behind the power of soft computing.